Hi folks, welcome back to Physics with Captain Rod. I'm making this one to help you with numbers 15 and 16, Unit 2-2. So let's start with number 15. It says in a particular town, electrical energy costs $15.15 per kilowatt hour. This number is in red in the homework, which means your numbers might vary, but that's the one I'm looking at. How much does it cost to operate a 75 watt bulb for 24 hours? So first of all, let's talk about the kilowatt hour here. Hopefully we understand what that is. But so power is energy over time. And if you rearrange that, right, energy is power times time. Anything that's a power times a time is de facto a unit of energy. If I were to take, say, a 5 horsepower motor, and we know it's running at 5 horsepower, and just multiply it by 10 minutes, I get a number of 50 horsepower minute. I could also, if I wanted to, multiply it by the same time in seconds or whatever, as long as you're consistent with your units. Anything that's a power times a time is de facto an energy unit. So a kilowatt hour. This is how electrical energy is normally built. And what it's equal to is kilo means 1,000. Watt is a joule per second. Hour is 3,600 seconds. And this comes out to be 3.6 times 10 to the 6 joules. So basically, the electrical company charges you 15 cents for this many joules. Now, why isn't it just so many cents per joule? The kilowatt hour is just a very convenient way to express electrical bills. It makes it very easy for figuring things out. Let me give you a quick example. Let's say I ran a 1500 watt heater for 2 hours. Now, 1500 watts is 1.5 kilowatt times 2 hours gives me a number, 3 kilowatt hours. That's how much electrical use I had. And then at this rate, I would take my 0.3 kilowatt hour and just multiply by $0.15 per kilowatt hour. And that's going to give you a number in dollars. By the way, if you want to write this as 15 cents per kilowatt hour, it's perfectly fine. So that's basically what you're going to do in Part A. They gave you a number. Mine says 75 watts. I would write that in kilowatts. That'd be 0.075 kilowatt. Multiply by the number of hours. And that's going to give you a number with units of kilowatt hours. And then you just apply your price to it. Number B is basically the same. Oh, I guess there's a little difference here. All right, hold on. Let me get rid of this and write down B. Okay, so B says a modern LED bulb can emit as much visible light as the 75, but it only draws 9.5 watts of power. Now, the 9.5 is in red. Your number might be different, but I'm going to use my 9.5. Write that in kilowatts. That'd be 0.0095 kilowatt. Then just multiply by the number of hours they talk about. That's going to give you a number in units of kilowatt hour. And then multiply by your price. Now, by the way, let's chat about this. You might wonder, is this magic? A 9.5, the LED bulb draws only 9.5 watts, and it says puts out the same light as the other one, which is 75 watts. This almost seems like magic. Like, how can this be? Well, it's because, and we'll talk about this later in the semester, more about light, but this 75 watts, a 75 watt bulb is how much power the bulb draws and uses. But a lot of this is not creating visible light. A lot of this is creating what's called infrared, that stuff that our eyes can't see, and a lot of it's just making the bulb hot and making the air around it hot. So only a small percentage of the 75 watts actually is visible light, whereas the LED doesn't get hot or anywhere near as hot. Basically, a much, much higher percentage of the used energy is used to convert to actual light. So it's just much, much, much more efficient. Anyway, that should get you through A and B. Let me look at C. A particular electric oven requires a potential of 220 and draws 20 amps. Okay, so in number 11, they give you a voltage, 220 volts, and an amperage, 20 amps. So power is the product of the two. Current times voltage. So multiply these out and get a power. That's going to come out in watts. Then I would convert it to kilowatts. And then multiply by the number of hours. I'll put n hours here to get a number, which has units of now kilowatt hour. And then you can use your cost factor on it. So that's definitely enough on number 15. Let's chat about 16. Let me get rid of this stuff first. Okay, number 16. Let's see. Let's talk about a cell phone measured in milliamp or milliamp hours. Milliamp hours. Rated for a milliamp hour use. Okay, what quantity does this measure? I don't want to give this away, but just take this, right? So milliamp hour. They're asking for what is this a measurement of? And it doesn't have anything to do with a milli. If you want, let's write this as 10 to the minus third or 0.001. And then write this in its most fundamental sense. And then write this in its most fundamental sense. And then multiply them. And something will fall out of that. You'll be able to do some divisions and something will fall out. I'll let you do that to answer part A. Part B, consider a battery rated at 4,000 milliamp hour. Now the 4,000 is in red. You probably got a different value, but I'll go ahead and write 4,000 milliamp hour. Milli means 10 to the minus third, by the way, so you could just write this as 4 amp hour, same thing. Looking for part B here. The battery voltage is given. Mine says 3.9 volts. Yours probably says something else. How much energy in units of kilowatt hours is stored? Okay, so remember, right, this right here is the electric potential. And remember how electric potential is defined, right, as potential energy per unit charge. See how knowing the definitions allows you to write these formulas out. Quickly rearranging it, it's real easy to see. Move this over here. That charge times potential is an energy unit. Right? It is in fact a potential energy. When you get the answer to the first part and you have this, you'll be able to calculate the potential energy stored in this thing. And they want it expressed in kilowatt hour. Well, earlier in this video, or maybe in the previous one, I talked about how to get a conversion factor. I'll go ahead and do it again. All right, take a look at 1 kilowatt hour and just take it at face value. Kilo means 1,000. Watt is a joule per second, and an hour is 3,600 seconds. This here is your conversion for going back and forth between joules and kilowatt hours. All right, I'm going to just leave that enough on that one. That should get that problem well underway here. I think I'll just end this and start a different one. All right, everybody have a great day.